Hi, and welcome to section 5, Stacking Models Together. In this section, we are going to look at overview of stacking technique, implementing blending in Python, and how to use stacking by implementing it in Python. So let's start with the overview of stacking technique. In this video, we will cover introduction to stacking, how stacking works, and an alternate stacking technique called blending. Stacking, sometimes called stack generalization, involves training a learning algorithm to combine the predictions of several other learning algorithms. First, all the other algorithms are trained using the available data. Then, a combiner algorithm is trained to make a final prediction using all the predictions of the other algorithms as additional inputs. To understand what this means, let's see with the help of a diagram. Here, we have an input data of size m cross n. This training data then goes inside different models. Then, we take the prediction from these models and combine them to form a new matrix. This matrix is of size m cross m, where capital M is the number of models. This data is then used for the second level model. M, where capital M is the number of models. Used for the second level model. And then the second level model makes the final predictions. So one of the important steps here is to create the training data for the second level model. So let's understand how that is created. We split the training data into k-fold, just like k-fold cross-validation. A base model is fitted on the k-1 parts and predictions are made for the kth part. We do this for each part of the training data. The base model is then fitted on the whole training dataset to calculate its performance on the test set. We repeat the last three steps for other base models. Predictions from the train set are used as features for the second level model. The second level model is used to make predictions on the test set. To further understand this, let's look at it with the help of a diagram. Let's take a look at this diagram. Here, we have the original data, which is then divided into train dataset, validation dataset, and test dataset. We keep rotating the validation dataset and get predictions on the validation set for all the training data. We also use the model built on the training data to make predictions on the test dataset. So now we have two tables which looks like this, where the first table is a prediction on the validation set for each model, M1, M2, M3 and M4, and the target variable from the validation set. The second table is a predictions on the test data, but here we do not know the target variable. So now we will train using the predictions on the validation set as its target variable, and then make predictions on the predictions of the test set. Blending is a similar approach to stacking. In the case of blending, we divide the data into train and validation set instead of k-fold validation. The other steps pretty much remain the same. We train the base model on the training set. We make predictions only on the validation set and the test set. The validation predictions are used as features to build a new model. This model is used to make final predictions on the test set using using the predictions value as features. In this video, we saw how stacking and blending works.
Creating an ensemble of learners is one way to make the learners you've got better. So we're not talking about creating a new algorithm, but instead assembling together several different algorithms or several different models to create an ensemble learner. One thing I want to emphasize here is that you can take what you learn here about ensemble learners and plug it right into what you're already doing with your KNN and linear regression models. Now, what we've been doing so far is we've had one kind of learning method, say KNN. We plug our data into there and we learn a model. We can query our model with an X and it'll give us a Y. So this is not an ensemble learner, this is just a single learner. And the idea with ensemble learners is that we have several additional learners. So we might have a linear regression based model, we might have a decision tree based model, we might have a support vector machine based model. You could continue this on with any different number of algorithms. They're all trained using the same data, and so now we have, in this case, 4 different models. To query this ensemble of learners, we query each model by itself and combine the answers. So if we want to query this model with X, we plug X into each model, the same X, and then our Y's come out. So we have a Y output from each of these models. How do we combine them? If we're doing classification, where, for instance, we're trying to identify what the thing is, we might have each of these Y's vote on what it is. But we're doing regression, and so the typical thing to do here is to take the mean. And that is the result for this ensemble learner. We can then test this overall ensemble learner using this test data that we set aside. Why ensembles? Why do we use them? Why might they be better? Well, there's a few reasons. First of all, ensembles often have lower error than any individual method by themselves. Ensemble learners offer less overfitting. The ensemble of learners typically does not overfit as much as any individual learner by itself. Now, why is that? Here's at least an intuitive answer, is each kind of learner that you might use has a sort of bias. It's easiest to talk about that in terms of linear regression, in terms of what do I mean by bias. So clearly, with linear regression, our bias is that the data is linear. KNN has its own kind of bias, decision trees have their own kind of bias. But when you put them together, you tend to reduce the biases because they're fighting against each other in some sort of way. Anyways, that's what an ensemble learner is like if we use multiple types of learners.
So Katie, you told everybody about training and test sets, and I hope people exercise it quite a bit. Is that correct?
Yes, that's right.
So now I'm going to talk about something that slightly generalizes this, called cross-validation. And to get into cross-validation, let's first talk about problems with splitting a data set into training and testing data. Suppose this is your data. By doing what Katie told you, you now have to say what fraction of data is testing and what is training. And the dilemma you're running into is you'd like to maximize both of those sets. You want to have as many data points in the training set to get the best learning results. And you want a maximum number of data items in your test set to get the best validation. But obviously there's an inherent trade-off here, which is every data point you take out of the training set into the test set is lost for the training set. So where do you set this trade-off? And this is where cross-validation comes into the picture. The basic idea is that you partition your data set into k bins of equal size. So for example, if you have 200 data points and you have 10 bins, very quickly, what's the number of data points per bin? Quite obviously it's 20. So you would have 20 data points in each of the 10 bins. So here's the picture. Whereas in the work that Katie showed you, you just pick one of those bins as a testing bin and the other 9 as a training bin. In k-fold cross-validation, you run k separate learning experiments. In each of those, you pick one of those k subsets as your testing set. The remaining k-1 bins are put together into the training set. Then you train your machine learning algorithm, and just like before, you test the performance on the testing set. The key thing in cross-validation is you run this multiple times, in this case 10 times, and then you average the 10 different testing set performances for the 10 different holdout sets. So you average the test result. 10 run the as a test. So you would have 20 data points. You just pick one of those bins as a testing bin and the other 9 as a training bin. In k-fold cross-validation, you run k separate learning experiments. In each of those, you pick one of those k subsets as your testing set. The remaining k-1 bins are put together into the training set. Then you train your machine learning algorithm, and just like before, you test the performance on the testing set. The key thing in cross-validation is you run this multiple times, in this case 10 times, and then you average the 10 different testing set performances for the 10 different holdout sets. So you average the test results from those k experiments. So obviously this takes more compute time because you now have to run k separate learning experiments, but the assessment of your learning algorithm will be more accurate. And in a way, you've kind of used all your data for training and all your data for testing, which is kind of cool. So let me just ask one question. Suppose you have a choice to do the static train test methodology that Katie told you about, or you do, say, 10-fold cross-validation, CV. And you really care about minimizing training time, minimize runtime after training, using your machine learning algorithm to output past the training time, and maximize accuracy. In each of these 3 situations, you might pick either train test or 10-fold cross-validation. Give me your best guess, which one would you pick? So for each minimum training time, pick one of the 2 over here on the right side.
Hello all, today we are going to discuss about XGBoost, which is also called as extreme gradient. Boosting. In my previous video, I've already discussed about something called as ensemble technique. Now in ensemble, right, which is nothing but a group of models, has two different types. One is bagging and the other one is something called as boosting. In my previous video, I've already explained about random forest, which is a kind of bagging, right? We discussed about both random forest classifier and random forest regression.
Hey guys, and welcome to yet another fun and easy machine learning algorithm on random forests. The random forest algorithm is one of the most popular and most powerful supervised machine learning algorithm that is capable of performing both regression and classification tasks. As the name suggests, this algorithm creates the forest with a number of decision trees. In general, the more trees in the forest, the more robust the prediction, and thus higher accuracy. To model multiple decision trees to create the forest, you are going to use the same method of constructing the decision with the information gain or Gini index approach, amongst other algorithms. If you're not aware of the concepts of the decision tree classifier, please check out my other lecture on decision tree GOT for machine learning. You will need to know how the decision tree classifier works before you can learn the working nature of the random forest algorithm. To create the forest, you are going to use the same method of constructing the decision, with the information gain or Gini index approach, amongst other algorithms. If you're not aware of the concepts of the decision tree classifier, please check out my other lecture on decision tree got. And welcome to another fun and easy machine learning tutorial on decision trees. A decision tree is a type of supervised learning algorithm that is mostly used in classification problems. A tree has many analogies in life, and turns out it has influenced a wide area of machine learning, covering both classification and regression trees, otherwise known as CART. Please join our notification brigade by subscribing and clicking that. Please join our notification brigade and regression trees, otherwise known as CART. And regression trees, otherwise known as CART. Please join our notification brigade by subscribing and clicking that bell icon. So a decision tree is a flowchart-like structure where each internal node denotes a test on an attribute, each branch represents an outcome of a test, and each leaf or terminal node holds a class label. The topmost node in a tree is the root node. In decision analysis, a decision tree can be used to visually and explicitly represent decisions and decision making. As the name goes, it uses a tree-like model of decisions. So the advantages of CART: it is simple to understand, interpret, and visualize. Decision trees implicitly perform variable screening or feature selection. It can handle both numerical as well as categorical data. It can also handle multi-output problems. Decision trees require relatively little effort from the user for data preparation. And nonlinear relationships between parameters do not affect the tree performance. The disadvantages of CART, however, is that decision tree learners can create overcomplex trees that do not generalize the data well. This is also known as overfitting. Decision trees can become unstable because small variations in the data might result in a completely different tree being generated. This is called variance, which needs to be lowered by methods of bagging and boosting. Greedy algorithms cannot guarantee to return the globally optimal decision tree. This can be mitigated by training multiple trees, where features and samples are randomly sampled with replacement. Decision tree learners also create bias trees if some classes dominate. It is therefore recommended to balance the dataset prior to fitting with the decision tree. If we look at some applications of the decision tree, we can predict whether a customer will pay his renewal premium with an insurance company. So you can predict yes if he will or no if he won't. You can use it to predict Titanic survival statistics. So if male or female as well as age, what are the chances of survival? You can use it to determine if a person is male or female based on their height and weight. Also, you can use it to determine a price of a home based on how many rooms as well as the floor size. A decision tree is drawn upside down with its root at the top. So in the image, let's look at the primary differences and similarity between classification and regression trees. Regression trees are used when the dependent variable is continuous. Classification trees are used when the dependent variable is categorical. In the case of regression trees, the value obtained by terminal nodes in the training data is the mean or average response of the observation falling in that region. Thus, if an unseen data observation falls in that region, we'll make its prediction with a mean value. In cases of classification tree, the value or class obtained by the terminal node in the training data is the mode of observation falling in that region. Thus, if an unseen data observation falls in that region, we'll make its prediction with a mode value. So the splitting process is continued until a user-defined stopping criteria is reached. For example, we can tell the algorithm to stop once the number of observations per node becomes less than 50. So in both cases, the splitting process results in fully grown trees until the stopping criteria is reached. But the fully grown trees is likely to overfit data, leading to poor accuracy on unseen data, and thus brings pruning. Pruning is one of the techniques used to tackle overfitting. We'll learn more about it in future lectures. So how can an algorithm be represented as a tree? For this, let's consider a basic example that uses the Titanic dataset for predicting whether a passenger will survive or not. This model over here uses three features from the dataset, namely sex, age, and number of spouses or children along. We can abbreviate this to SIB, SP. In this case, whether the passenger died or survived is represented as red and green text respectively. Although a real dataset will have whether a passenger will survive or not. This model over here uses three features from the dataset, namely sex, age, and number of spouses or children along. We can abbreviate this to SIB, SP. In this case, whether the passenger died or survived is represented as red and green text respectively. Although a real dataset will have a lot more features, and this will just be a branch in a much bigger tree, but you can't ignore the simplicity of the algorithm. So what's actually going on in the background? Growing a tree involves deciding on which features to choose, and what conditions to use for splitting, along with knowing when to stop. As a tree generally grows arbitrarily, you need to trim it down for it to look beautiful. So let's start with common techniques used for splitting. So how does a tree decide where to split? So the decision for making strategic splits heavily affects a tree's accuracy. The decision criteria is different for classification and regression trees. Decision trees use multiple algorithms to decide to split a node in 2 or more subnodes. The creation of subnodes increases homogeneity of resultant subnodes. In other words, of subnodes increases homogeneity of resultant trees. Decision trees use multiple algorithms to decide to split a node in 2 or more subnodes. The creation of subnodes increases homogeneity of resultant subnodes. In other words, we can group our data in regions based on data that have similar traits. Decision tree splits the nodes on all available variables and then selects the split which results in the most homogeneous subnodes. We'll tackle an example soon in this lecture. The algorithm selection is also based on the type of target variables. So let's look at the 4 most commonly used algorithms in decision tree. 1. Beauty index. 2. Chi-squared. 3. Information gain. 4. Reduction in variance. So we'll not go into detail on these algorithms, as some involve quite a lot of math, and most of the hard work is done within scikit-learn's libraries. Let's gain an intuition of how splitting the data would work if we had to do it manually. So over here we have arbitrarily generated data. We have x1 and x2, which are our independent variables. If we had to look at this data, we can split it into 5 regions. So we can draw a line here at x1 equals 20, as well as x2 equals 50. And then another one over here at x1 equals 25. And then a last split over here between by x2 equals 30. So we have regions R1, R2, R3, R4, and R5. And we do this empirically. The algorithms I mentioned earlier will do this for you. Now remember, you can split it a bit further into more regions. So say for example, we can split R4 over here, and that will result in more subnodes in our tree. But for now, let's just have 5 regions. So we start off over here at our root node. So we ask ourselves, is x1 less than 20? So we go either yes or no. So if yes, is x2 less than 50? So if you look at our graph over there, and then we separate that into R1. So if yes, we have R1, if no, we have R2. Then we go to our other branch and we ask, is x1 less than 25? So over here we look at if it's less than 25. If yes, then it's R3. If no, then we ask ourselves, is x2 less than 30? And if yes, we got R5, and if no, we got R4. So as you can see, that is really simple. So this is all the basics to get you on par with decision tree learning. Decision trees are also very useful when used with other advanced machine learning algorithms like random forest and boosting, which we shall cover in future lectures. A popular library for implementing the algorithm, scikit-learn. It has a wonderful API that can get your model up and running in just a few lines of code in Python. So thank you for watching. Please don't. Then we go to our other. We ask over here, is R4? So as you can see, that is really simple. So this is all the basics to get you on par with decision tree learning. Decision trees are also very useful when used with other advanced machine learning algorithms like random forest and boosting, which we shall cover in future lectures. A popular library for implementing the algorithm, scikit-learn. It has a wonderful API that can get your model up and running in just a few lines of code in Python. So thank you for watching. Please don't forget to smash the like button and click that bell icon to become a part of our notification brigade. And also support us on Patreon. See you in the next lecture. For machine learning, you will need to